So what if you were asked to take a Boolean expression like this one and turn it into a waveform or a timing diagram? So if we take a look at our function here, we can see that it's basically just a simple two-input OR gate. Two-input OR gate. And that's because in Boolean algebra, the plus sign represents the OR operation. So if we were to take a second to just draw this out as a circuit with logic gates, it would simply just be you have two inputs A and B, and you're putting them through an OR gate to get your output F, which is going to be A or B. So that's really what we're dealing with here. So the first step for this would simply be to construct a truth table. So we have two variables here. We have two variables. And so that means we're going to have 2 to the power of 2, which is 4 different rows in our truth table. So we're going to set up A, B, and F as our columns, and we're going to have 4 different rows. So the way that I like to set up a truth table is I'll take the first variable and I'll split it kind of down the middle with zeros and ones. So since we're going to have 4 total rows, I'm going to do 2 rows of zeros and 2 rows of ones. The next one, I like to take the halves that I just made and then split them in half. So since there's 2 zeros and 2 ones, I'm going to put 1 0 and 1 1 here because I've just divided that section in half. And then here I'm going to put 1 0 and 1 1. Again, just divided that half in half. And that concludes the part of the truth table for A and B. So now let's go ahead and take a look at F. We know that F is just a simple two-input OR gate. And based on what we know about the OR gate, we know that it's only going to have an output of 0 when both of the inputs are 0, which means this first row is going to be 0 and every other row is going to be 1. So that's our truth table for this Boolean expression right here. So how would we turn this into a waveform? Well, in order to get set up with that, we can take a look at the truth table we've constructed here. We have 3 columns. We have 3 columns, which means we're going to have 3 waves. And we have 4 rows. We have 4 rows, which means we're going to have 4 sections or intervals on our waveform diagram or our timing diagram. So here's how you would basically set up the waveform diagram for this, or the timing diagram. So as you can see, there are 1, 2, 3, 4 different intervals, and that corresponds to the 4 rows in our truth table. And there are 1, 2, 3 different waves, and that's going to correspond to our 3 different columns in our truth table. So we can go ahead and start putting this together. So the first row is going to correspond to the first section of this waveform diagram. So here we can see in this section, A is 0. And let's just take a look at A first. Let's draw the waves one at a time. So in this first section, A is 0. In the next section, A is still 0, so we're still going to leave it at 0. In the next section, it becomes 1, so we're going to go up and draw it as 1. And in the final section, it is also 1. And as you can see, the same way that in the truth table, I decided to kind of take the 4 and split it in half between 0 and 1, you can see that visually here too. This is kind of half, and this is half, and we've split it down the middle between 0 and 1. And you can label this if you'd like 0 and 1 here, and I can draw those for all the other waves as well. And often you'll hear people refer to this 0 as a logic low, and the 1 as a logic high. And that kind of goes back to the idea that in a waveform, this part is low because it's 0. This part is high because it's 1. So now we've drawn our waveform for A. So let's get started on drawing the waveform for B. So in the first row here, B is 0. So that means in our first section, B is going to be 0. In the next one, it's going to be 1. So we're going to go up, and it's going to be 1. In the next one, it's going to go back down to 0. So we're going to go back down. It's going to be 0. And in the final one, we're going to go back up to 1. And as you can see, again, we've taken the half and split it in half, just like I mentioned with the truth table. And again, take the other half, split it in half to get the waveform for B. So now that we have the waveform for B and A, we can go ahead and make the waveform for F. So for F, we know that in the first row, it's going to be 0, which means in the first section, it's going to be 0. And then after that, it's always 1. So it's going to go up to 1. It's going to go up to, it's going to go up to 1. And then for the rest of this timing diagram, f is going to be 1. So this would be the timing diagram that corresponds to this truth table and this function. And just a conventional thing to note as well, people will often draw the waveforms for the variables above the waveforms for any functions that are in terms of those variables. And that's simply because if you were given a graph or a waveform diagram or timing diagram that consisted of these two variables, you could look at them and kind of see how they interact in order to produce the function that is in terms of them. For example, here you can see A is at a low and B is at a low. And since 0 and 0 is going to produce a 0, then your f function, 0 or 0 will produce a 0. Then you know that your f function, which is A or B, is going to take two 0 inputs and it's going to be 0 there. And everywhere else, there aren't any other places where both A and B are at logic low at the same time, which means that everywhere else, your function, A or B, is going to be at a logic high. All right, so let's try this example here. So again, let's take a look at our function. We have not A and B. So if we were to draw this out as kind of a circuit diagram, we're going to have some input A, we're going to have some input B. We're going to have to take A and run it through a NOT gate in order to get not A. So on this wire, you're going to have not A, and B is just staying as it is. And both of these are going to be fed as inputs into an AND gate. And that's going to get you your output F equals not A and B. So that's how this would look on a circuit diagram. So let's go ahead and construct a truth table for this expression. So even though we have this variable not A, we're going to make a column for not A, but it's not going to introduce new possibilities the way that a third variable would. So we still have two variables, and that means we have 2 to the power of 2, which is 4 rows in our truth table. So let's go ahead and construct the truth table. We're going to have a column for A, a column for B. Actually, you know what? I'm going to put the column for not A next to the column for A. Then we're going to have a column for B and a column for F. And remember, even though we have 4 columns, the not A column isn't introducing new combinations of zeros and ones into the mix. So it's really not going to contribute to the different possibilities, and it doesn't really count as a third input variable. So taking a look at this, we can do what we did last time. We're going to have 4 possibilities still. So we can take the first variable and just split it down the middle. We're going to do 2 zeros and 2 ones. Not A is just going to be the opposite of A. So we can take this and simply just do the opposite. We're going to have 1, 1, and then 0, 0, because not 0 is 1, not 0 is 1, not 1 is 0, and not 1 is 0. So then for B, we're going to take the halves and split them in half. So we're going to go 0, 1, 0, 1. So we've taken the 2 halves and kind of cut them down the middle now. And then we can take a look at F. So F is slightly more complicated this time, but also not really. It's just a 2-input AND gate. It's just a 2-input AND gate, except this time we're going to make sure that we want to look at the right columns to figure out what our inputs are. So in this case, we're actually just going to pretty much ignore this A column when we're calculating F. We're only going to look at the not A column and the B column because those are our 2 inputs into our function. So if we take a look at these 2 columns and use them as inputs, we can remember that the AND gate is only 1 when both inputs are 1. That means that it's only going to be 1 here in this row, where not A and B are both 1, because that would mean that both of its inputs are 1, and as a result, its output will be 1. Everywhere else, it's going to be 0, and that just comes from the AND operation. So now we have our truth table for this Boolean function. So if we take a look at this, we have 4 rows, which means we know we're going to need 4 sections on our waveform diagram. And we have 4 columns. We have 4 columns. And in this case, that actually does mean we're going to have 4 waveforms. We're going to have 4 waveforms because usually in these types of diagrams, you want to include both a waveform for A and a waveform for not A, just to make everything explicitly clear when you draw your waveform for F. All right, so I've gone ahead and done the setup for this timing diagram. Just like last time, we've got our variables A, not A, and B, and we've got our function F down here. And here we have the logic high state and the logic low state represented for each waveform for each variable. So we can go ahead and kind of translate our truth table over to the timing diagram. So here we know our first row is going to correspond to the first kind of section or interval in our timing diagram. So let's go ahead and start with the waveform for A. So in the first row, we can see the waveform for A is going to be 0. In the second row, which means the second section or interval in the timing diagram, it's still 0. In the third and fourth rows, which means the third and fourth intervals in our timing diagram, it's going to go up to 1, and it's going to stay at 1 for both of those intervals. So as you can see again, it's like taking the 4 and we've just split it in half with 0 and 1. Not A is simply going to be the opposite of A. You don't even really have to explicitly look at the truth table. You can just look at the wave and you can figure out what you need to do. Since A is 0 this entire time, as long as A is 0, not A must be 1. So you know that it has to be at a logic high for the first two intervals. And then as soon as A switches up to a logic high, you know that not A has to switch down to a logic low because it's going to be the opposite of A. So you can conclude that it needs to be 0 for the last two intervals. And there you have your waveform for not A. Alternatively, you could have looked at the truth table and said, well, it's 1 in the first two and 0 in the second two. But I find just looking at the wave sometimes is a bit easier, especially just for complementing variables. So for B, we can take a look, and again, we know we've taken the halves and split them in half with zeros and ones again. But if you want to look at the truth table, then you know B is going to start off as 0 in the first row, which corresponds to the first interval. Then it's going to change to 1 in the second row, which corresponds to the second interval. It's going to go back down to 0 in the third row, which corresponds to the third interval. And it's going to go back up to 1 in the fourth row, which corresponds to the fourth interval. So now that we have our waveforms for A, not A, and B, we can try to construct our waveform for F. So if we look at our truth table here, we know it's going to be 0, and then 1, and then 0, and then 0. So in the first row, F is 0. That means in the first interval, it's going to be 0. Then in the second row, i.e. the second interval, it's going to go up to a 1. And then for the last two rows, which correspond to the last two intervals, it's going to stay at a logic low at 0. So this would be the timing diagram that corresponds to that Boolean expression. All right, so let's try to do a bit more of a complicated example now. So what if we wanted to represent this function here? So the first thing we can do is just examine this again. We can see that we've got sort of an AND expression within a bigger OR expression, and this one is complemented here. If we were to draw this out as a circuit diagram, well, we're going to have some input A, we're going to have some input B. Both of these are going to get run through an AND gate because we want to get A and B. So if we run them through an AND gate, the output on this wire here is going to be A and B. And then we have some input C, and we want to get not C, which means we need to run C through a NOT gate or an inverter. And now on this wire, you're going to have not C. And then both of these are going to become inputs to an OR gate in order to perform this addition operation in the middle there. And the output of this OR gate is going to be your function F. It's going to be AB or not C. And that's going to be your function F. So this is how you would draw that sort of as a circuit diagram. So let's get started on constructing a truth table. So we have 3 variables this time. We have 3 variables, which means we're going to have 2 to the 3 means 8 rows in our truth table. So we're going to have a column for A, a column for B, a column for C, a column for not C, and a column for F. And again, just like last time, we're separating C and not C. Just by convention, it's better to have a waveform and easier, especially with a more complicated function like F, to calculate F when you can directly look at a column and see what the zeros and ones look like instead of having to kind of flip something in your head. All right, so that in mind, we're going to do the same strategy we did last time. It still applies with 8 rows. So this time, since we have 8 rows, we're going to do 8 over 2 is 4. So we're going to split it 4 and 4 with zeros and ones in our A column. So we're going to have 4 zeros, 1, 2, 3, 4, and 4 ones, 1, 2, 3, 4. So as you can see, we've started our 8 rows and we've split it kind of half and half with zeros and ones in our first variable. So for B, we're going to take those halves and we're going to split them in half again. So now we're going to go 2 and 2. We're going to go 2 zeros, 2 ones, 2 zeros, 2 ones. So we've taken those halves and we've kind of split them in half. And now for C, we're going to take these halves and we're going to split them in half. So now we're going to be alternating 0, 1, 0, 1, 0, 1, 0, 1. And for not C, we're simply just going to take the opposite of whatever C was. So where C is 0, not C is 1, and vice versa. So we're going to end up going 1, 0, 1, 0, 1, 0, like so. And now we need to calculate F. So F gets a bit tricky, simply because there are a couple different operations to keep in mind. So let's make sure first that we're looking at the right columns. Our inputs to F are going to be A, B, and not C. So we're going to ignore the C column when we're trying to calculate F. So the way that we're going to do this is we're just going to break it down into different steps for each component of F. So if we were to kind of write out F for each of these rows, the first row, we know F is AB plus C. So in the first row, we're going to have 0 times 0 plus 1. In the second row, we're going to have 0 times 0 plus 0. And we can actually shorten this process a lot. We know A is going to be 0 for all 4 of these, so we can put 2 more zeros down here. And we know it's going to be 1 for the last 4, so we can put 1s down here. And since we're doing A times B, we know B is going to be 2 zeros there, and it's going to be 2 1s here. So we know it has to look like this. We know it's going to be 2 zeros here, so it has to look like this. And we know it's going to be 2 1s here, so it has to look like this. And then for C, we know, or for not C, sorry, we know it's going to go 1 0, 1 0, 1 0, 1 0. So we can simply add on our alternating 1s and 0s like so. So now we have our expressions for F filled in with the values from the truth table, and we just need to calculate what F will end up being. So the first thing that we can look at is this AND expression here. The multiplication in Boolean algebra represents the AND operation. So if we take a look at the AND expression and we remember what we know about AND gates, we know that the AND operation is only going to be 1 when both inputs are 1. That means these 2 rows here. These 2 rows here are the only rows where both of your inputs to the AND operation are going to be 1. Everywhere else, there's either one input that is 0 or both inputs are 0, which means in all of these places, you don't have a situation where both inputs are 1, only down here, which means that only for these bottom 2 rows will you have a 1 in that first part of the expression. And we're just going to leave the OR part untouched for now. That means all of these ones is going to be 0. And then we're just going to leave the OR parts untouched as they were, just with alternating 0s and 1s. So now we've narrowed it down to this, and we can take a look at the OR expression. What we know about the OR expression is that the OR expression is only going to be 0 when both inputs are 0. That means here, and here, and here. So if we simplify this even further, we know that the only time this is going to be 0 is when both inputs are 0, so we can go ahead and fill those in. And everywhere else, you're going to have a 1. So this is really the column that represents your function f. This is the output of f. And this is what we will use to draw the waveform for f. So we can go ahead and set up the timing diagram. So just taking a look at this, we know we have 1, 2, 3, 4, 5 columns, which means we're going to have 5 waves. And we know that we have 8 rows, which means we're going to have 8 intervals or sections in our timing diagram. All right, so I've gone ahead and done the setup for the waveforms just like before. So as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8 different intervals in our diagram, and that corresponds to our 8 rows in our truth table. And we're also going to have 1, 2, 3, 4, 5 different waves, and that corresponds to the 5 columns in our truth table. And again, I've drawn on the logic high and logic low states for each of the variables just to make labeling extra clear on the timing diagram. So we can go ahead and start off by constructing a waveform for A. Just looking at this, we know, okay, we've got split it down the middle. We've got 4 intervals that are 0 and 4 intervals that are 1. We've kind of split it right down the middle. So we know that what we can do just looking at the truth table for A is we can have it at logic low until the 4th interval, and then bring it up to logic high for the last 4 intervals. Because what we've essentially done is split it down the middle in our truth table, and it's the same thing that we're going to do in our waveform diagram that represents the truth table. If you wanted to go row by row, then you can recognize, okay, first, second, third, and fourth row are all 0, which corresponds to these 4. And then 5th, 6th, 7th, and 8th row are all 1, which corresponds to these 4. Now looking at B, again, we know that we've taken the halves and we've split them in half. So you can simply look at this diagram and go, okay, we're going to go 0, 0, and that's half of 4 is 2. So we're going to go for the last 2, 1, 1. And then we're going back down. We're going to go 0, 0 for half of this part, and then 1, 1 for the remaining half of this part. So as you can see, we've taken the halves and split them in half. But if you wanted to go row by row, you can say first and second are 0, third and fourth are 1, 5th and 6th are 0, 7th and 8th are 1. And then for C, again, you know you're taking those halves and splitting them further in half. So you know you're going to end up going 0, 1, 0, 1, 0, 1, 0, 1. Because you've taken the halves, which were 2, and you split them in half. So you're going to go 1 by 1. Looking at the truth table, you can also see that you're just alternating 0s and 1s, but if you wanted to go row by row, you can use this to correspond to the first section, this to the second, this to the third, etc. Now, not C is simply going to be the opposite of C. So without using the truth table at all, we can take a look at this and go, wherever this is 0, not C has to be 1, and wherever this is 1, not C has to be 0. So we're just going to do the opposite of the C waveform. So here it's going to be 1, it's going to go down to 0, going to go up to 1, down to 0, up to 1, down to 0, up to 1, down to 0. So now we have all of the waveforms for all of our individual variables, and we can start drawing the waveform for F. In this case, it is a lot easier to just look at the truth table where we did the calculations already than to look at the waves and try to back calculate F in your head for each specific interval of the diagram. So looking at our truth table, the first section is going to be 1. The second section is going to be 0. The third is going to be 1. The fourth is going to be 0. The fifth is going to be 1. The sixth is going to be 0. And then the 7th and the 8th are both going to be 1. And if you wanted to look at the waveforms and kind of see why this is the case, you know that everywhere where both of the inputs are going to be 0 for an OR gate is going to result in a 0, and wherever basically anywhere else, it's going to be a 1. So if you wanted, you could look at A and B and not C and kind of back calculate it by looking at when these waves are at a logic high or low. Personally, I find it easier to just do the calculations for a more complicated function like this in the truth table and then plot the waveforms like so. Another option that you could do as well is instead of just jumping straight to F, you could also plot waveforms for AB, and we've already plotted it for not C, but you could plot a waveform for AB as well, and that'll make it easier to take a look at the AB waveform and the not C waveform and simply perform an OR operation on those two. So it just depends how thorough you want to be in the diagram. So the last thing that I'd like to go over is how to construct a waveform for a given function if you weren't really told anything about the truth table and it occurs at weird intervals like this that aren't kind of even and nicely spaced out like the ones that we were using before. If you're given two waves like this and you're told what the function should be, you can look at the waves and construct the function based on your knowledge of Boolean algebra. So looking at this, you know that this is A times B, and this is the AND operation. That means you're going to have A and B being fed into some AND gate, and F is your output. So you know about the AND operation that the only time it's going to be 1 is when both inputs are 1. So you can take a look at both of these waves and ask yourself where both of them are equal to 1. So here we can see A is 1 and B is 1. So as long as A and B are both 1, F is going to be 1. As soon as even one of them drops to 0, F is going to drop to 0. So here we see both of them are 0. That means that F is getting 0, 0 as input. It's going to be 0. Here, we can see that they both go back up to 1 for this very short interval, which means that f is going to follow them up to 1 because both inputs will be 1, so the AND operation will produce a 1. Here we see that a is 0 and b is 0 for this interval. So we're going to have this at a logic low for that entire time because both of them are 0. Then here a transitions to 1, but b is still stuck at 0, which means the AND operation is still going to produce a 0 output. But as soon as we hit this interval right here, we can see that b goes up to a logic high and a is at a logic high, which means that f is going to follow it because both inputs are 1, and that's going to go on until you hit this interval here. The reason it stops here is because a goes back down to 0, so even though b is at 1, the AND operation is still going to produce a 0, and that's going to carry on until a returns back to a logic high, b is high, a is high, which means that f is going to follow them up. And if we pretend that this was a straight line when I drew it, until here, f is going to be at a logic high because both of the inputs are at a logic high. And then finally, they both go down to a logic low, so f is going to follow it down to a logic low. And that's how you would construct the waveform if you were given two other waveforms and asked to construct a waveform for some function of those two inputs.